Hey everybody, this is Module 1, Lesson 1.02, describing data. So whenever we get a bunch of data, and it's just a stack of numbers, we want to try and make sense of it, just because just staring at the group of numbers really isn't going to give us a whole lot. So our procedure for figuring out what our data kind of looks like or how we should organize it, we got to remember our SOCs, okay, SOCS. And S stands for shape. So what we mean by shape is our data all symmetric? Is our data right skewed, or is our data left skewed? I want to talk a minute about right skewed and left skewed distributions, because these get confused all the time. And the reason is because in a right skewed distribution, a lot of common mistake is you'll see a bunch of data more towards the left of your grouping. So you'll be tempted to say, oh, this is a left skewed distribution. That's not how we determine skew. To determine which way our data is skewed, we have to look at the tail. So the right skewed distribution has a tail going to the right. In other words, there is some piece of data or a few data points more to the right that's kind of stretching our graph more to the right. So if you want to know which direction your skew is, look for where your tail is. So if your outlier, well, I don't necessarily say outlier, if our tail is on the right, it is a right skewed distribution. If our tail is on the left, it's a left skewed distribution. So that's S. O stands for outliers. So a lot of times if we're taking data, an outlier is something that just doesn't quite fit. Okay? Everything else seems to fit into a pattern, and then an outlier just is out there on its own. In terms of taking a bunch of numbers, statistical measurement of numbers are outliers, or sorry, a way to measure that, we're going to look at interquartile range, and I'll explain that later. So really it's if we're past 1.5 times the interquartile range. C stands for center. There are two methods of measuring center. Median, which is pretty much just the center of the data. It's the center number. Okay. And mean, which is the average. Now, one of these is more prone to, or has better resistance to outliers than the other. So when we talk about resistance, we mean how resistant a number is, sorry, not a number, a value is to outliers. In other words, if we were to throw an outlier into our data, is it going to pull or skew that value more or less? So as we'll see, a median is very resistant to outliers. Okay? If I throw another number into my data set that's a big outlier, chances are it's not going to shift the median very much. However, it could very much shift the mean. So we got SOC. S, our last S, is spread. So this is a talk about how spread out is our data. Is it all kind of crunched together in the middle, or does it spread out over a large area? The simplest measure of spread is range. And the way we find range is just simply maximum minus the minimum. It's a very quick, very odd look at how our data is spread out. Variance and standard deviation. So range is also very much vulnerable to outliers, so it doesn't have a very good resistance. So we always want to find data that has good resistance to outliers. So instead of just using range, which kind of, okay, so we know our maximum, minimum, and the spread between that, we want to know what is each data point like? How is that on average different from the mean? And the way we do that is we calculate variance and standard deviation. In other words, actually we essentially take our standard deviation is basically just an average, or sorry, just a per a correction of variance. So, well, let's talk about it in terms of an actual set of data. Okay, so let's say we've got a class of 30 students, and we want to analyze the data. Oh, very important. There's two different equations for both variance and standard deviation. Okay, and they have different letters, or sorry, representing them. So, if we're talking about a population, that means we sampled everybody in the population. We questioned everybody in the population. We use this Greek letter here, which is a lowercase sigma. And our formula for standard deviation is, well, what we're going to do is we would take every single data point, we would subtract it from the mean, or we'd subtract the mean from it, we would square it, and then we would divide that by the total number of values that we have. So if you imagine, if I have 30 students and I want to define standard deviation, well, I would first find the mean, the average, and then I would take each one of those points. So I would take 21 and subtract the mean, which we're representing with the Greek letter mu. So make here mean. If we have a population, the entire population, we use mu. If we're just taking a sample from the population, we use x bar, so x with a little bar over it. Okay. In this case, we're using the entire population. We have the entire class here. So we would take 21, subtract whatever the average is. Okay, we would calculate that first. And then we would square it. And the reason that we're squaring it is that our average is going to be somewhere here. Actually, we'll pause on that one. Let's take a few steps back before we actually start calculating standard deviation. I don't want to get too deep into this yet. Let's just take a look at our get our 5 numbers and set up a box plot. Okay. So, first thing, let's find our minimum and our maximum. Well, I've actually taken the liberty and organized all of our scores from lowest to highest. Okay, so that's nice. That makes finding the minimum pretty easy. That's just going to be 21. Our maximum is also very easy. That's going to be 99. To find our median, well, that's going to be the middle number. Well, I've got 30 students. That means that I'm not going to actually have a middle number. I'm going to have 15 and 15. So my median is actually right in between right in between 80 and 81, which means I would take the average of those two, which would be 80.5 would be my median. Okay. Next, we need to find our first quartile and our third quartile. Our first quartile, well, to find that, we actually find the median between the minimum and our median, so the middle number between our first set here. Well, we know there's 15, so we know that there is going to be a middle number, so it would, halfway between 15 would be 7.5, so it's really going to be the 8th number. So 1, 2, 3, 4, 5, 6, 7, 8. There's our first quartile, Q1. And my third quartile, same thing. It's going to be the middle of these numbers, so 1, 2, 3, 4, 5, 6, 7, 8, so 87. This will be our third quartile. And from here we can actually draw a box plot. So I'm just going to mark these down. So Q3 on our number line is here. Q1 was 66. Right about here. Our median. Oop, put the Q3 in the wrong spot. Q3 is 87, so that's closer here. There we go. Median was 80.5, so just right about here. Our minimum is 21. And the maximum was 99. So I can put a box around my first and third quartile with the median in the middle, and then these become my whiskers. Okay. So right off the bat, now we can take a look at, we can start off with analyzing our socks. So let's take a look at spread. So is this a symmetric, or is it left, more left leaning or more right leaning? Okay. So remember, the left skewed would mean that we would have a tail going to the left, and a right skewed would mean we'd have a tail going to the right. Well, where's our tail at? It looks like it's more to the left, so this is a left skewed data set. Okay. All right. Outliers. So I mentioned before this 1.5 IQR. Well, IQR is interquartile range. So our interquartile range is the difference between our first quarter and our third quarter. So in this case, our interquartile range would be 87 minus 66, which gives us 21. Okay, that's our interquartile range. But to figure out an outlier, what we do is we would say 1.5 times our IQR, which is 1.5 times 21, which equals 31.5. So what I want to do with this 31.5 is I want to take that and add it to my third quartile and subtract it from my first quartile and see if there's any data points that are past that. So if I take '87 plus 31.5, well, I get 118, and there's definitely no data that's past 118. 99 here, this maximum is not an outlier. Okay? Let's go the other way. Let's take 66 minus 31.5. Well, we get 34.5, which is right about here. So this minimum actually is an outlier. Okay, it's something that's definitely we want to take a look at. So outliers, once they're identified, it really depends on what you want to do with your data. Sometimes we want to analyze the outliers. Sometimes if we can identify them as something that we can remove and then study the remaining set, sometimes we can do that. But for now, all we're doing is just identifying them. So we have one outlier to the left, and that is 21. Okay, center. Well, we already identified the median. Okay, our median is 80.5. That is the middle of the data. Okay, half of our data is above that, half of our data is below that. The other measure of median is mean, which is average. So if I wanted to calculate that, I would add up all of these numbers and then divide by 30. Oh, that's a pain. Gosh, and then going on to standard deviation, oh my gosh, that would be even bigger pain. So luckily we have technology that can do that for us. Well, let's actually go ahead and do that. So I'm going to go ahead and open up Desmos.
Ready to go, Sharp? Good.
I already have some data here. I have our data here listed. By the way, if you want to create this chart, all you do is you hit this plus, and then you add table, and then you can add your data. Let's get rid of that. Okay. So I have all of my data here, all of our scores. Okay. I want to find average. Okay. Well, what I do is I click on this little keypad here, and I go to functions, and I go to mean. And I type in, while I put everything into y1, so type in y1, and we get 75.5. So our mean, since this is a population, so we're going to use the Greek letter mu. And we get 75.53. Repeating. All right. So we got our center. By the way, the fact that our mean is pretty good ways from our median tells us this also is left skewed. So we're getting a pull from this outlier. That's why our mean is getting pushed left of our median. it's a little less resistant to outliers than a median is. Okay, we got our center. Last one, spread. Well, our range is our max minus our min. So our range would be 99 minus 21, which equals 78. So range gives me a fairly broad sense of the spread. So 78, that just tells me that my data is spread out between 78 percentage points of between 0 and 100. Well, that's a pretty good spread considering the lowest we could potentially have is 0 and the highest we could get is potentially 100, assuming there's no extra credit. We want a better idea of spread. We want to use standard deviation. So our standard deviation is going to tell us how each one of these data points on average is different from the median, or how much it deviates from the median, or sorry, the mean. So if I wanted to do this by hand, I would take 21, my first data point, 21, minus 75.53. Okay, that would tell me a deviation from the median. Okay, and let's say I did the same thing for starting at the other side. I took 99 minus my mean. Well, the problem with this is that this is going to give me a negative number. This is going to give me a positive number. And ultimately, when I sum them up to try and take an average, it's going to all cancel out. And I'm going to get essentially 0. And I'm not going to learn anything about this spread. So mathematicians came up with a way to fix this. And the way that they're going to fix this is we are going to square these values. Okay? If we square these values, then no matter what, they're going to come out to be positive. So after we square all these differences, and we're not going to go through and do every single one. Okay, you'd have to do 21 minus 75.53, do 49 minus 75.53, and so on, so on, so on. We get all those values, and then we divide it by the total number of values, which is 30. We're going to get an average deviance from the median squared, and we call that value variance. Okay. Variance gives us some idea of how much we're spread, but because it's a value that is squared, it's going to be the further numbers that are more like this 21 is going to have a much bigger squared deviance than deviation from the middle than, let's say, the 80 would. Okay, it's going to get much more exaggerated. So we fix that by then taking the square root and that gives us standard deviation. Now you notice that there's two different formulas for standard deviation versus of a population and standard deviation of a sample. Okay, and the main difference, well, the only difference actually, well, there's two differences. One is the letters that they use. So again, if we're dealing with the population, we use mu for the letter for our average. If we're taking the average of a sample, we use x bar. It's just as a symbol. It's still the same idea. Other differences is that sigma is the representation of the population standard deviation, and S is the sample standard deviation. Okay. So why does the sample standard deviation then have n minus 1? So in other words, after we're taking the average, let's see the same thing in the variance. After we're taking the average of variance, why do we not why do we do n minus 1 on the sample size? In other words, we're dividing into it less by one less of our total value. If this was, for example, our 30 count here of data, if this was a sample instead of the entire class, we would be dividing by 29 instead of 30. Now the reason we do that, well, the proof is actually a not too bad of a calculus example, but you have to use calculus in order to prove it. But to just give you an idea, if I was going to take a sample out of this set, chances are I'm not going to get both the minimum and the max. In other words, my spread is going to be artificially shrunk because I'm probably going to pick more from the middle than to get the total spread from left to right. And so what this n minus 1 is it's simply a correction. Okay? It corrects us to get a better value for both variance and standard deviation that gets us closer to the true value if we're trying to estimate what the population is by taking a sample. Okay? You don't need to worry about what that proof is. Just know that the difference between when you're taking a population and when you're taking a sample. Most of the time in statistics we are taking a sample, but not always. Alright, so real quickly I will show you how we can use Desmos to find the other statistical values that we need. Okay. So we got mean here. I want standard deviation. Well, there's two here. There's standard deviation and there's standard deviation P. We want this one because this is the population. Again, and for this example, we have the entire population. So put that in, and then our standard deviation is 16.2. We can also use Desmos to find our 5-number summary. So we go to function under stats and we go to minimum. There's our minimum. We can do the same thing for our first quartile. So we put quartile y1, and then if we want our first quartile we have to hit comma 1. If I want my median, there's two ways I can get that. I can actually do the same thing I just did, but put quartile 2, that's actually our median, another name for our median, or I can actually just click on median, and it gives us the same value. If I want my third quartile, y1 comma 3, there's my third quartile, and I can get my max as well. So there's my 5-number summary, okay, as well as mean, standard deviation, all very easy. Alright, that's it, and I will see you next time.